Sorry I couldn't come to Israel to give this talk. My topic is history of the vector potential. Most of the content of my talk have already appeared in this article by Alfred Wu and myself. The vector potential was introduced by many people in various contexts. Of these, Thomson and Stokes were perhaps the most important. In a letter dated in 1850, Thomson wrote to Stokes, "My dear Stokes, do you know that, etc., etc., that, etc., etc., is what is now called the Stokes law or Stokes theorem. We all know that that is the foundation of differential geometry." Maxwell wrote 3 papers. The second paper was published in 5 installments. Commonly, it is thought that paper 3 is the most important. People usually call that the origin of Maxwell's equations. Actually, Maxwell's 2 key ideas were in the first 2 papers. In the third paper, he only put the 2 together and created the name of field theory. If we look into Maxwell's first key idea in paper 1, it was the idea about how to understand Faraday's electrotonic state. The electrotonic state, was a vague idea which Faraday had believed in, but was unable to clearly define because Faraday did not know very much of mathematics. In 1881, years after Faraday and Maxwell were both gone, Helmholtz had this to say: Faraday found that an electromotive force striving to produce these currents arises wherever and whenever magnetic force is generated or destroyed. He concluded, that means Faraday concluded, that in a part of space traversed by magnetic force, there ought to exist a peculiar state of tension, and that every change of this tension produces electromotive force. This unknown hypothetical state he called provisionally the electrotonic state, and he was occupied for years and years in finding out what this electrotonic state was. In 1856, Maxwell found the answer to this puzzle, and that was that the electrotonic state was the vector potential. In modern notation, we would write E equal to minus A dot. He published this in paper 1. He was 26 years old. That he knew he had landed on something important, and that it might lead to disputes about credit, he was very aware of. So at the end of the paper, he had this paragraph: with respect to the history of the present theory, that means electrotonic state is equal to A, I may state that the recognition of certain mathematical functions as expressing the electrotonic state of Faraday and the use of them in determining electromagnetic potentials and electromotive forces is, as far as I am aware, originally. This is, in my opinion, a completely fair statement. But the distinct conception of the possibility of the mathematical expressions arose in my mind from the perusal of Professor W. Thomson's papers. You see that here Maxwell was very careful. He did borrow from Thomson the idea of the vector potential. So he was afraid that Thomson might take offense. That's why he made the statement. But in Thomson's papers, although there were extensive uses of the vector potential, Thomson never linked that with Faraday's ideas of the electrotonic state. So the credit should go to Maxwell 100%. Thus to Maxwell, A is central to his understanding of electromagnetism. That is probably why in all his later papers and in his books, he never illuminated the vector potential. But now, before we go on, let me mention a puzzle. Maxwell knew that the vector potential was not uniquely defined. So we should ask, which choice of A in modern language, which gauge did he select to be the electrotonic state in writing this, in formulating this formula at the bottom? If you want to search through that paper, one of his, this is the paragraph which has some bearing on this puzzle. Maxwell wrote, "We have now obtained in the functions alpha 0, beta 0, gamma 0, that means the components of vector potential, the means of avoiding the consideration of the quantity of magnetic induction which passes through the circuit. Instead of this artificial method, we have the natural one of considering the current with reference to quantities existing in the same space with the current itself. To these, I give the name of electrotonic functions or components of the electrotonic intensity." The emphasis in red were Maxwell's original one. This is the only paragraph in which perhaps Maxwell was really referring to the different gauges. This paragraph seems to suggest that he chose a gauge where A is inside of the electric wires. If so, does there exist such a gauge? Does there exist such a unique gauge? All of these questions Maxwell never mentioned. And this remains perhaps an important subject for the historians of science to look into. Be that as it may, it is clear that the vector potential being identical to Faraday's idea of the electrotonic state was Maxwell's great first discovery in his paper 1. Then in his second paper, the key idea was the displacement current. This has been well discussed in recent literature. This is again a very puzzling development, because as I said earlier, paper 2 was published in 5 installments called the part 1, then part 2, then part 3, then part 4. And it was only in the 4th installment, part 3, where the displacement current occurred. In earlier parts of this paper, you find the diagrams, intricate diagrams like this, with vortex motion. These are very intricate. What was clear was Maxwell was struggling to find a mechanical model to explain the vector potential in the electrotonic state. Then suddenly, in the 4th installment, we find the following paragraph. Proposition 14. To correct equation 9 of part 1 of electric currents for the effect due to the elasticity of the medium. This correction was the addition of the displacement current. So puzzle, another second puzzle. How did Maxwell arrive at this correction? This is a question that I've studied for some time and did not know, did not explain. Maxwell evidently, in the first 3 installments, struggled to make a mechanical model that he thought would, in some sense, be the analog of electromagnetism. In the process of this, perhaps when he tried to study the question of charge conservation, I don't know, maybe when he landed on the idea of trying to explore the question of charge conservation, when he realized that he needed to add an additional term. This, in my opinion, is another great puzzle in the history of physics. After Maxwell's death in 1879, Heaviside and Hertz independently presented Maxwell's equations with A eliminated. Heaviside especially was extremely happy with this elimination. He said in 1889, the psi and A are murdered. Psi is the scalar potential. The psi and A are murdered, so to speak, with a great gain in definiteness and conciseness. In 1892, he said, the duplex method being the method using E and H without A, the duplex method eminently suited for displaying Maxwell's theory and brings to light many useful relations which were formerly hidden from view by the intervention of the vector potential and its parasites, the parasite being the scalar potential. Of course, we all know that indeed it is true. After we eliminate the vector potential, the equations look more symmetrical with respect to a dual transformation exchanging E and H. And that evidently was one of the reasons that greatly delighted Heaviside. So after Heaviside and Hertz, there existed a dogma. The dogma says electromagnetism resides in E and H. Where E and H are 0, there is no electromagnetism. This became a dogma, and in the first 60 years of the 20th century, this was what every student of physics was trained in. When I was a student in China, and later a graduate student in Chicago, this was the thing that we all learned. Then came 1959, the great paper of Aharonov and Bohm, the paper that we are gathered here today to celebrate. Their proposed experiment was finally done by Tonomura et al. Quantitatively. That experiment was a decisive one which shattered the age-old dogma and revealed the true importance of the vector potential. And that is that in quantum mechanics, E and H under-describe electromagnetism. Only knowing E and H is not enough. Even when E and H are both 0, there is still possible electromagnetic effect. On the other hand, if you take the loop integral of the vector potential over all loops, that over-describes electromagnetism. In other words, you do not need that much of information to realize all the electromagnetic effects. It is this expression which, over all closed loops, that correctly describe electromagnetism. Thank you.